Hello, and welcome to this episode of Midnight Math, where we do homework number 3 for Math 110. Let's just get started. So let's see. So problem 1, find all the natural numbers m such that m, or modulo m, these two numbers are congruent. Now there's just a footnote reminding us what that is, or like what that notation means, because we use two different notations in this class. This compact one, which I like a lot of times because it puts it right on the actual relation itself, and also the parenthesis pmod version. Both have their uses. Anyway, so a lot of the problems that we were solving in class were about what happens if there's a variable that's congruent to something else, but this one is the modulus is the variable. So one thing we can do is rewrite this as using the definition. So using the definition of congruence, this is equivalent to finding all m in the natural numbers such that, oops, that was a double S, m divides 2022 minus 1965. I'm not sure why I chose 1965 again. Let's see, where's the textbook? Here you are. I have a feeling it was like the copyright date. No, this was 1969 and 1978. What a mystery. Because I definitely was not born in 1965. Okay, well anyway, I'm not really feeling like doing that subtraction in my head. So I'm just gonna pull up an overpowered calculation device for this. So 57. So 2022 minus 1965 equals 57. And the factors, maybe this is why I chose 1965, because I think 57 is the Grothendieck prime, where he thought it was a prime number because he didn't really like examples. Or that's the story I heard. Because this thing is well, 5 plus 7 is 12, right? So it's divisible by 3. Yes, and 18. That is a prime. Okay, that explains 1965. I think 2022 is clear. Okay, so 3 and 19 are prime divisors. So, hence, m can be in the set of 1, 3, 19, and 57. Because we're only looking for the natural numbers, and also once we have all the prime factors, we can just take any amount of each of them. Oh yeah, one thing I forgot to say, in the other videos I always said, well, hopefully this doesn't take more than an hour. So I think I have to say that again. It's starting to be a tradition. We'll see how it goes. Okay, so that's rendered. Well, let's think about insignificant formatting considerations. I think it would look nice set out as an equation. Okay. Solve the system of congruences. X is congruent to 2, mod 3, 5, and 7. And there's this sort of obscure thing trying to tell you what not to, like how not to cheat. Like, here's what I was trying to avoid. Here, I'll write the solution set. not following the instructions. So I just take these. I need to get rid of these dollar signs. Because dollar signs are how you enter and leave math mode in tech, which LaTeX is built on. So that's what I didn't want. Just saying, well, you know, the solution's the solution. Like, what else is there to say? So I just want, what we talked about in the lecture is that a solution of a system of congruences is when you bring it down into a single congruence. It's a good enough form for most purposes. So, so that's not satisfying that yet. Also, I don't know what happened, but this turns out to be a trivial thing to solve, in a way. Well, yeah, well, it's not completely trivial. Here, let's solve it the easy way. The one where it just seems a little too clever, but it's more of like a mistake on my part. So notice that x equals 2 is a solution to this system. Yeah, it's a lot more interesting when the residues are different. But when they're all the same, we can just take that number as the residue, because, you know, 2 mod 3 is 2, mod 5 it's 2, and mod 7 it's 2. So one thing to then say is, by the Chinese remainder theorem, since 3 and 5 are coprime, which remember means their GCD is 1, then we can combine those into a single congruence. So by the way, there is a version of the Chinese remainder theorem that can handle multiple congruences simultaneously. So if for some reason you're not in Math 110 and you're watching this, that's why we're doing it this way. It's easier to explain than sometimes use. But yeah, let's see. So we combine the first two. And then also 15 and 7 are coprime. So again, by CRT, which I'll just write as that here. One thing, okay, so when we talked about this theorem, one thing that, what happened there? I didn't write 2. One thing that is part of the proof is how you calculate this number, or like how you can calculate it. But really, that's just to prove it exists. The statement of the theorem is that if there is a number that exists with this property, I mean, like, let's see. Like, if you can find a number that that whenever x is congruent to it, then it's congruent to these other congruences hold, then this is the only number it could be. It's this uniqueness result. So since 2 just worked, then I can just use 2 without needing to calculate anything else. But, you know, we could get our hands dirty with Béziers identity and all that to calculate one. Okay, well, so let's follow the thing. It says, hence, let's see, the solution set are the set of all x in Z such that x is congruent to 2 modulo 3 times 5 times 7. Yeah, so that's that. I still haven't figured or gotten around to looking at how to get the indent or the new line to look good there. Because the thing about writing up things like this is I usually don't use LaTeX in this way, so it's always sort of ad hoc to come up with something for this, because I'm usually just like writing a paper, not all these fancy green boxes. Okay. Also, the reason it says a list of residues, I'll put this in parentheses. What could have happened is we could have gotten a bigger modulus. Like say 2 times 3 times 5 times 7. Then the solution set would be of all x in Z such that x is congruent to 2 or okay, so whenever you have a modulus that's divisible by another modulus, you can reduce your congruence to that smaller modulus. But if you go the other way, then when you lift a solution up, then what happens is the quotient of the two moduli gives you the number of solutions that appear. We covered that whole thing about like how many solutions does a linear congruence in one variable have. So it's the same thing, or like one of the ways that we proved it was by this sort of observation. So yeah, so if we had, I'm going to put potentially, just to strengthen that, like, there's no reason you would have. So we potentially could have gotten a bigger modulus, and then the solution set would be all the integers, where x is congruent to one of these two residues. So modulo 3 times 5 times 7, that's 0. So both residues are congruent modulo that number. But modulo this, we've got these two. I kind of think of this as being like there's this clock where we go through 3, 5, 7 once, and then we go through 3, 5, 7 again. And there's a 2 on the first way around, and then the next 2 the next way around. And the significance of this clock going twice is it's, I guess, like a 24-hour clock versus a 12-hour clock. On a 24-hour clock, you have the AM and the PM part. But on a 12-hour clock, you just go through AM then PM. So anyway, these are the two times continuing the analogy in 24-hour format, where in this first thing we just did it in 12-hour format, where in the end we only know the answer mod 12. Okay. Hopefully I don't ramble too much while I'm giving these solutions. So let's give a description of the set of all x such that 3 divides blah blah blah. And this time it's asking in the form of a set like that, where it's a plus bn for n in integers. So notice that this is equivalently the set of all x in z such that x is congruent mod 3 to 2, x is congruent mod 5 to 2, and x is congruent mod 7 to 2. I've always found this a little confusing, that equiv gives the congruent symbol, but congruence, or cong, gives us a completely different symbol. That's usually used for isomorphisms. Okay, so then by part A, we got that x is congruent mod 3 times 5 times 7 to 2. So, using the definition, is this a well, let's say using the, so this was a lemma in lecture, but using the definition of congruence and divisibility, then solutions are those x and z for which there exists a k in z such that x is equal to 2 plus 3 times 5 times 7. I'm just going to put that in parentheses and not worry about it. Okay. Right, because that's what it means for x and 2 to be different by a multiple of 3 times 5 times 7. And then this is actually exactly what that notation means. So, hence, the solution set is 2 plus 3 times 5 times 7 k, where k is in the integers. Okay, so that's problem 2. Let's go on to problem 3. We've got a bunch of linear congruences to solve. It's some calculation, but gotta show you that calculation. Well, one funny thing is, like, 19 isn't so big, so we can just check 0 through 18 what solves it, and then by theory we know that we've solved it. Okay, so let's do A and B together because it's the same modulus. So for A and B, we have that, let's count how many solutions there are. So, like, 19's prime, and 2 is between 0 and 19 exclusive. So anyway, that means that its GCD is 1, so certainly that divides. And also 3, for the same reason, divides 1. So both have exactly one solution. Well, what do I mean? Well, they have one solution modulo 19, which is a weird statement. So to an abstract algebraist, they'd be like, yeah, that makes sense because we use this quotient construction for dealing with numbers modulo something. But in this class, we've actually been dealing with integers. And there are infinitely many integer solutions to this, but they're all different from each other by a multiple of 19, and that's the sense in which there's exactly one. Okay, so should we just sort of guess? Because, like, So because we're going to do the principled way for part D. So non-principled observation. This is just ad hoc. So the thing I noticed is 2 times 18 is, oh no, I'm at 2 times 9 is 18, which is, well, so 2 times minus 9 is, okay, 18 is 19 minus 1. So 2 times minus 9 is congruent mod 19 to 1. Yeah, so the solution is x is equivalent or congruent mod 19 to minus 9. Well, that's a fine solution. If we wanted, we could add 18 to it to get a residue. I'll just do that. So add 18 to minus 9. Wait, did I even do that right? I just want to make sure. Yeah, okay. Oh, we're adding 19 to it, right? So 10. I'm going to add a footnote. Just like these things are easy to check. So 2c dot 10. Oh, why did I do it in such a weird way? But I'll show you why I think this is weird. Because, so 2 times 10 is 20, which is 1 more than 19. So that's 1. So 10 really is the... Okay, let's not do crazy stuff. Well, first I'll show you how that renders. Oh, wow, okay, the footnote goes right in the solution. Yeah, so anyway, 10 is the multiplicative inverse of 2 mod 19. Let's do our non-principled observation, which is that 20 is 19 plus 1. So 2 times 10 is congruent to 1. Hence the solution to this is 10. And you can get anything that's any multiple of 19 plus 10 is the solution in this way. Okay, so can I just, well, 20 is not a multiple of 3, so we can't do that same trick. But 18 3 times 6, let's say minus 6 is minus 18, which is 1 minus 19. Hence 3 times minus 6 is congruent mod 19 to 1. So the solution to B is x is congruent mod 19 to minus 6, which we can also if I'm able to add 19 to this, which is add, okay, 13. So this is if we want to represent it as a residue. Okay, that went wrong. What did I do? I did conger, which is not a real thing. Okay, the next one is a little more interesting. For C, we have that 4, 6. The GCD of that is 2, which divides 18. So there exists 2 solutions modulo 18. The lecture gave a way to just write the solutions down, basically, well, once you find one solution. But another thing we can do is reduce this. So we can reduce this congruence to the equivalent 2x is congruent mod 9 to 6 by dividing everything by the GCD. Just checking I did that right. Okay, so now 2 and 9 are coprime, which we expect because, well, we divided by their GCD. So, can we just guess the solution again? So we want 2 times something is 3. If we add 3 to 9, so 3 is equal to, well, 3 is congruent mod 9 to 3 plus 9, which is 12. And 12 is 2 times 6, so there's only one solution. So that gives us the solution. This is why it's nice to have some theory, because you can calculate things the wrong way and then know that you got an okay answer. You didn't need to do it right. You know, you didn't have to go through an algorithm where the algorithm, because there's some algorithms where just because, like, they've been proved ahead of time that they give the right answer, but it's nice knowing properties to not have to do the algorithm. I guess I may as well mention how to, or I should say also, if we want to represent this in the original modulus, and this goes back to that like the earlier problem that we talked about, which is you know, the 24-hour clock. So if we want to represent this in the modulus, it would be x is congruent mod 18 to 6, or how do I want to? Well, we usually write like x equals like 1, 2, 3 in solutions. So, so 6 plus 9 is 15. Well, okay, let's not belabor this. Like to get these numbers, you can also do the Euclidean algorithm, which we're gonna do now for the next problem. I don't want to calculate, or let's see what this is gonna look like. So 9 1984, the GCD of it, and 20 is 4, and 1984, does that, yep, that is divisible. That's good. So first, let's do this reduction. So the GCD of 20 and 984 is 4, and 1984 is 4 times 496. So there exists 4 solutions modulo 1984. Let's reduce the modulus. So reducing the by dividing by the GCD, we get the equivalent. Okay, so 20 divided by 4 is 5. 1984, this is why I wrote it with that dot so I could remember its quotient. And then 984 I did not calculate. 246. Okay, so by this calculation, we know that the GCD of 5 and 496 is 1. So applying, so we want to find x and y in the integers such that 5x plus 496y equals 1. So to do this, we apply the Euclidean algorithm. I thought it looked really gross how it turned out last time. I was thinking, we can make a table. Let's try that. That'll be fun. We can figure out how we're going to do this tabular. So I was thinking of having columns A, B, and A mod B. Let's start with that. So we've got A, and these letters are just so that we know what we're talking about. And so we'll put the larger number first, I guess. This is not going to be a long algorithm. It's only going to be a few steps. So we start with 496 and 5. And then we want, actually, you know, we want a bunch of data here because we want the extended algorithm. So let's also record the quotient. So, I'm not going to do the arithmetic. I forgot, is diff mod a thing? guess not. A lot of languages have a div mod operator that give you both the division and the remainder simultaneously. So 496 over 5 is 99. But we also want mod. That's 1. Okay, this was pointless. But let's look at how it looked. And I get my lefts and rights mixed up too often. Yeah. Really, that should be centered, but the numbers, I wanted them to line up by place value. Yeah, the reason I'm saying that this is pointless is that, well, we can see that the GCD must be 1 right now, but let's continue. Maybe it won't be so pointless. So we take the GCD taking a larger number. Oh, this is an interesting thing. I wonder if you'll all be able to follow it. So, one way that we've seen it is like we keep swapping. Oh yeah, okay, we are doing the swap. So the 5 goes here, and then in a way the 496 goes there, but after reducing. But in this way, it like jumps over the 5 to remainder, and then both of the numbers go diagonally. Okay, so now the remainder by 1 is just, 0. And then the quotient is 5. So anyway, I'll just, why not? Okay, so one reason I was building this table was because I was thinking it might be a good way to record some of the coefficients. Because it's sort of another way of doing this calculation. But I haven't really done it before, like this. So, right, so there's the GCD, it's 1. And like what we're trying to do is say, okay, like 1 of this and 0 of that gives us 1. And then how do we then use that fact along with this data here, these two lines, to then say that some amount of this plus some amount of that is 1? So the GCD just okay, so we got that. So now what? I'm going to just start by writing 1 is 0 times 5 plus 1 times 1, which is 0 times, right, so what was this 1? It's this remainder, which is 496 minus 99 times 5, which is equal to minus 99 times 5 and 1 times 496. Well, I guess that's that. because then these are the coefficients. This is why I said it was pointless earlier, because we already got it by getting that remainder of 1. Well, I'll just leave this as is. And okay, we want to find this. We want to just find sum. So x equals minus 99 and y equals 1 suffices. To 5x plus 496y equals 1. Now what? Well, the point is that hence why did I use x and y? Let's change this to a and b, because we're already using x. Okay. Hence, 5a is congruent mod 496 to 1. So we have, well, I guess we didn't talk about multiplicative inverses yet by this point, but so let's say, like, I want to use a and multiply both sides of this by that. Just thinking of how can I justify that. Well, we have x is congruent, or I'm going to use p mod notation this time. X is congruent to (5ax) because it's congruent. 5a is congruent to 1, and 5ax is 5xa, which is equivalent to 246a. So x is congruent to minus 99 times 246 p mod 496. I'm going to leave a note here. The above reasoning is just that we haven't talked about multiplicative inverses by this point. Like, really, what we did is take both sides of this congruence by a, which is the multiplicative inverse of 5 modulo 496. So it cancels to the 5. And it's not clear what the above is supposed to mean. Just to clarify, I want to say it's this. Okay. Let's see, how are we doing? Good number more problems, and we're at 46 minutes. Definitely can be done in an hour. Okay, so yeah, I hope you enjoyed this problem about ISBNs. And I do think it's funny that the international ISBN agencies, the International Standard Book Number Agency, it's like an ATM machine. Let's delete that footnote for the solutions. So, yeah, so it's this cool little bit of number theory that's just sitting around us. It's also very similar to actually how the internet works. Every packet of data that goes through the network contains a checksum like this, but it's more than just a check digit. It's like I don't know. It's like either a 16 or 32-bit number, I think. Base 2. Yeah, so those are also whizzing all around us. But here's one that we can actually see by looking at a book. So, really, all that we need to know is that there's this congruence here involving 13 unknowns. So let's verify that the course textbook is valid. So we want to calculate. So we want the every other digit. Let's see, I'm just going to copy this down. Oh, and it's an ISBN 13 because there's also like, I think ISBN 10. I actually forget. It actually says most books have both. Yeah, it's an ISBN 10. And I thought about doing the problem for ISBN 10s. You probably can't see that. But the check digit is in base 11, and they use an X whenever that sums up to 10. Okay, so the course, I just thought that would make things confusing, so we'll just stick with base 10 for the ISBN 13. So the odd positioned digits are, I'm going to do this because I think it'll make it easier for me. Okay, so I deleted that one, and 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 that one. Okay, then the even position digits. So I guess we're starting with 1. That's not good. Let's try again. And I have a better idea of how to avoid a mistake. Yeah, they both ended in a 7, and there's only one 7, so it can't have been it. So, okay, so removing the evens. So delete 4, delete 4, delete 4. Okay, delete the odds. There we go. Okay, so then we take this, and we take this, insert a bunch of pluses, and we're doing this mod 10. So, yeah, I'm not going to do any fancy tricks. So one thing I do like doing is like taking the 9, for example, turning it into a -1 mod 10. A 7 is a -3, so those cancel out, for example. And like, I guess trying to make it be near 0. Instead of making it 0 through 9, make it like -4 to 5. That's another way that you can do this sort of arithmetic. So, thankfully, this is valid input from Mathematica. So that's 43. I'm just going to do it in steps because, you know, these are solutions, but like, you know, this actually is, like, you just calculate it. Like, any calculator can do this. So, but, you know, maybe you want to check the intermediate results. Oh, right. One thing I can do. That's nice. Also, now we can just do this in our head. 9 is -1, and 9 times, so -1 times 3 is -3, and then add 3, that's 0. Also, maybe to mix things up, I know I already typed it. Let's turn this into a p-mod. Oh, that looks... This is why I set things up in a line, because I can add these breakpoints easily. Now this is part of AMS math. That's what adds that environment. Probably don't even need to worry about it. Most templates start with it. Maybe that's a reason not to do it that way. Okay. We got 0 modulo 10, so the ISB N13 is valid. Okay, the professor had written down a valid ISBN 13, but its last digit is illegible. All you can read is this and then last digit. Oh, I didn't realize that you could select it. That's funny. I just used an I because it was the letter that made the box kind of a reasonable size. It's good I didn't put the actual number under there. So what must its last digit be? Well, let X stand for the illegible digit. The validity formula is, okay, and again, I'm going to remove the hyphens. Then those will be the odds, so I'll remove every other, should end in an X, then remove every other, starting with a 9, delete the X, create the align, take these, add the pluses, there's a 3 times in there, add the pluses, and then this is supposed to be 0 mod 10. Okay, so now doing the basic arithmetic. Yeah, when I was looking this up, I guess 978, I think that's the United States, books published there. I don't really remember. Yeah, so most books in the United States start with that. Oh, why did I type that? Because as we established before, I can just copy paste. So wait, that was 34? Yep, 34 plus x plus then this. $75. And let's reduce even more. I guess that was 25. Yeah, I'm just gonna. So 75 plus 34 is 109. Oh, I was just thinking, do I really even need that intermediate result? But, okay, so modulo reducing 109 to 9. Well, yeah, why not? So x plus 9 is equivalent to 0 mod 10. Like, one thing we can do is subtract 9 from both sides, or adding 1 both sides, using the old clock. We get that. So now the idea is, it's a digit. This means x equals 1. Well, it's only asking what the last. Oh yeah, therefore the last digit must be 1, since it's a valid number. Let's see. I think it's this book. 7223. No, that's the next problem. Maybe it's this one. Yeah, okay, so turns out this book is one of the number theory books I have around me for, designing lectures, building problems. Yeah, so it's 978-1441-930-941. Exactly what was predicted. Okay, the next one. It's like the same sort of deal. But the thing is, before... Oh, wow, I put a star? Yeah, where before it was x times 1, this time it's going to be 3 times x, so it's a little more exciting. Let x stand for the illegible digit. The validity formula is, let's take our number. Change that to an x, remove the hyphens, copy it, go through this thing again. Curious about doing a macro. Nah. Well, yeah, I'm gonna try. So Emacs lets me do macros. Okay, I need to start it off in the right spot. There we go. That took the same amount of time. So now we get this one. This simplifies to this. Actually, I can just type it in. Yep. Let's expand it. So 82 plus 3x. And this reduces to 2 plus 3x. And there are a couple things we can do. You know, we can calculate a multiplicative inverse of 3. Let's just mention that. So notice that 3 times 7 is 21, which is congruent mod 10 to 1. So if I'm going to also say, and hence 3x is equivalent to minus 2. So if we multiply both sides by 7, we get x is equivalent to minus 14, which is congruent to 6. Therefore, since 0 is less than or equal to x is less than 10, this means x equals 6, because it's a residue. Therefore, the last digit must be, or the penultimate digit must be a 6. And this book is, I'm pretty sure, Davenport's The Higher Arithmetic. And this one is 9780521722360. Math wins again against illegible handwriting. Last part of this problem. Now the last 2 digits are illegible. So can we recover? Okay, this is getting rather repetitive, but so let x and y stand for the second, or respectively stand for the second to last and last digits of the ISBN 13. So we got that. And let's start setting up this equation. I still got the macro, which saves so much time. So we're almost there with the setup. Only add another macro for the pluses. I guess I could have done that at the same time as the deleting. Okay. The validity formula is, okay, this simplifies to so let's see. (82 plus 3x plus y). So one thing to notice, for each x, if we plug it in, we can solve for y to get y is equivalent, or a congruent mod 10 to minus 3x minus 82. And I don't need to do this, but, you know, while we're here, this is 7x plus 8. Yeah, so, therefore, there are 10 valid ISBNs, 13 numbers that start with these 11 digits. So just for sake of seeing them, I guess, because I just kind of want to see them. Let's make a table. I'm thinking about how I want to format it. Okay, so I got, wrong environment. I just want a tabular. So left, 1, 2, 3, oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the first thing, I'm going to have x, and I'm going to have y. And we can solve for y, so I guess I'm going to make x be the dependent variable, 3 are independent. And then, okay, so this equation, we have two equations on hand. So every time x increases, okay, so when it's 0, we got 8. Then every time x increases by 1, one thing that we can observe is that the number decreases by 3 or increases by 7, mod 10. So I'm going to use decreasing by 3 first. So 5, 2. Now, decrease by 3, I can also add 7. So that's 9. Then decrease by 3, 6, 3, 0. I can add 7. Decrease by 3 is 4. And then 1. Guess that's clear enough. Oh yeah, so one thing in the design of ISBN why is there a 3? Why don't they just sum it all up? And why is it a 3? Well, one is 3 is co-prime to 10, so you can always solve for x. And that was actually a key here. Like, we found this modulo inverse because 3 was co-prime. But also, if you take, why is it even or odd digits and even digits? It's because if you accidentally transpose two numbers of the ISBN while you're typing it in, then it's gonna very likely cause this check digit to fail, or this validity check to fail. And so what we can see here is that these are, at least for this number, if we accidentally swap the last two digits, the only times that the two digits, if we swap them, we get another valid one, is when the two digits were the same. So like 0 and 8, it's 8 and 4. So like if the 8 moves, the other number changes. If 5 moves, the other number is different. That's fine. 9, it changes. 6, 5, 3, 9. Yeah, so anything swaps here, it's going to be invalid or the same ISBN. So that's kind of cool. It's interesting how math can help safeguard against human errors like that. Prove or disprove. So for all a, b, and m in the integers where m is positive, if a and b are congruent, or a and minus b are congruent, both mod m, then their squares are congruent. Well, doesn't that just seem like the usual squaring something makes the minus sign go away? So let's prove it. So let's see, suppose a, b, m in the integers are such that m is greater than 0, and suppose a is equivalent mod m to b, or a is equivalent mod m to minus b. So we have an or. Let's handle the two cases. So case 1, and the thing we're doing our cases on, I guess, is implicit here. Maybe that makes it clear. Okay, let's just set up both cases. So in the first case, we have that we can just prove this equationally. Pause was, I was deciding where to put the goal, and I've decided I'm going to state the goal after this, after the cases are done. So we have a squared is congruent mod m to I don't know, well, like we proved that when you, well, let's see. I'm not going to change it to this, but like the idea is a squared is a times a, and we can then replace each a with b and then put it back together. But it's also something that's easy to prove, that if you have an integer or a natural number power, then we can just plug it in, I guess. in lecture I called Modular Arithmetic, where you do the different congruence laws. This is part of the reason, I guess, like why writing this all up live, well, recorded, is it's an interesting challenge, because I'm like trying to decide how am I gonna write this in what I consider to be as clear as possible, while also explaining my thought processes and all of that. Let's say that. Okay, so we have a squared is equivalent to minus b by substituting by modular congruence, and that's equivalent to minus 1 squared well, like the thing is, minus b is just equal. I'm splitting this up to just like chaining equalities can get a little confusing if it's also has equivalences mixed in. It's nice knowing why things are true. Like I could say that these two are just congruent, but they're also equal, which is stronger, and that's easier to see what the reason is. Okay, so a is equivalent, a squared is equivalent mod m to b squared. Okay, so now, in both cases, we showed that, so therefore we are done. Therefore sounds silly there. Next one. Prove or disprove for all a, b, and m such that m is positive. If a squared and b squared are congruent, then either a and b were congruent or they're negatives of each other. That sounds a lot like, well, that's how it works for normal numbers, not modulo. So maybe it's true. Well, let's explore a little bit. I'm going to type some stuff. So a squared equivalent or congruent to b squared. This is equivalent to a squared minus b squared is equivalent to 0. Or it's equivalent to this. And this is equivalent to a minus b, a plus b. And to get these conclusions, we need m to have to divide one of these two sides. And like really the only way that this can happen in general is if m is prime. And so that's the problem. M's not prime. And that's why it's false. Yeah, because I guess we did show this was true. What was it that we were trying to show? I guess it also popped up in part of the proof of Wilson's theorem, I think, one version of it. Except it was when b is 1. Like numbers that are their own multiplicative inverses, modulo a prime. The only ones are 1 and -1 according to this when m is prime. So anyway, now that we've expanded this out, we can try cooking up a counterexample. And that is just, we need to find, so one way to make up counterexamples is to just guess random things and hope that something comes through. But sometimes by expanding definitions out like this, we can be like, okay, let's find two numbers where m divides their product, but it does not divide either of them. So m equals 4, like 4, 2, and 2. That would do it, right? So let's say that m equals 4, a minus b equals 2, and a plus b equals 2 for this counterexample. And then we can solve for a. That's 1, and b is -1. Right? No. A is, oh, there we go. A and b are 1. So let's disprove. Just want to, I always forget if it adds the dot or not. Okay, disprove. We will show that, and I'm doing this much wordier than we need to be. Part of why I'm doing this is you're used to the idea of finding counterexamples, but like what we're actually, when you find a counterexample, you're actually disproving something. Like you're proving its opposite, or a logical negation. So we'll show that there exists a, b, m, and z such that m is greater than 0. And a squared is equivalent to b squared. A is equivalent, oops. So we've got this or, so I want to say already be, I'll use but, even though it's this is a little, like it makes it seem like a counterfactual or something. I don't know if I'm making sense. So we use a equals 1, b equals 1, m equals 4. Okay, so we have that m is greater than 0. And a squared is equivalent mod m. Wait, what am I doing? Why is this going to be a counterexample? Oh, right. This is supposed to be not equivalent. Okay. So why is this bad? So I made it so a plus b was 2, right? But a minus b, I failed. I just can't solve equations. Okay. Add the equation. A is 2, b is 0. Guess I heard one of you screaming at your monitor. So keep it up. Okay, so a squared is congruent mod m to 4, which is a congruent mod m to 0, and b squared is I'm not going to mention the positive part, that's obvious, and it just clutters. So then b squared is equivalent to 0. Okay, that 4 was messing me up for some reason. All right. Therefore, we showed what we wanted to show. Just some filler words to say we're done. Okay, 6. For all a, b, and p such that p is odd and p is a squared plus b squared, then p is 1 mod 4. We're actually going to see later is that when p is prime and odd and 1 mod 4, then it's actually a sum of 2 squares. So we're showing that it's at least necessary. Wait, that's sufficient. Wait, which way? Yeah, well, if it's a sum of 2 squares, then it has to be 1 mod 4. But this is just for an odd number. There are a couple things we could do. We could just make a table of numbers, basically. So mod 2, when you square it, it actually ends up, the result mod 4 only depends on what it was mod 2. This is sort of a special case. Okay, I thought of something to deal with this. I was thinking of introducing like some extra notation or something. But, well, yeah, I'll introduce some new variables. Let's let q and q prime. No, we don't want a prime. Let's just do q1 and q2. We could just say what they are. It's a over 2, and q2 is b over 2, the floor. Because I was thinking, I don't know if this is going to work, so let's just take a look. Follow along. So we have that a squared plus b squared is equal to q1, or 2q1. That's why I did that, it's just so I can do this. Okay, so we got that. So we've got those remainders, and let's just square it. So we got 4q1 squared plus 4q1 a remainder 2 plus a remainder 2 squared. That's only 0 or 1, so it actually doesn't matter. It's always going to be the same thing as the unsquared version. So then we also have this all with b and q2. Let's see, how are we doing for space? Yeah, it's kind of ugly, but not so bad. So now we got all these things that are a multiple of 4, which is why this all works. So let's delete this 4. Then we got this part. Did I actually want to do that? Because what I could also do is just say that mod 4, it's just this last part. Let's just, we don't need to, like, you know, factoring out multiples of 4, those days are behind us now that we have congruence. Okay, so since remainders after dividing by 2 are either 0 or 1, which square to themselves, then what we have is that a squared plus b squared is this, where we have to remember that, like division, no, well, you know what? I'll just add the parentheses back so you don't even have to worry about what the precedence is. Because, you know, remainders are not in PEMDAS. Or PEM, whatever it is. Okay, so now okay, now taking this, oh wait, that's not equals. Yeah, so taking this modulo 2, then we learn nothing. Let's go back a little bit. Notice that modulo 2, a squared yeah, so I'll put this down here so I don't have to say that again. So, because of that, P is congruent mod 2 to a plus b. So now, what do I want to say? I'm going to say that because of p being odd, that means that, well, we called the addition table modulo 2. Now this is a very tabular day. Guess this doesn't really matter. Plus zero, 1, H line, 0, 0, 1, copy it, 1, 1, and now the only interesting part of this addition table, that 1 plus 1 is 0. Thus, for p, ooh, how did p, I did conjure again. I haven't even noticed. So for p to be odd, we need that either A is odd and B is even, or A is even and B is odd. So this is a place where we could use a without loss of generality, because everything is symmetric in A and B. We can just flip the roles of A and B, and so flip them there, and then by reordering the for alls and then using commutativity of addition, we have the exact same statement. So because these are the two cases, then well, you know, like we can just assume it's the first case. So anyway, the thing is, let's just not bother with that, because we'll go back to, we'll just say in either case, we have A remainder 2 plus B remainder 2 is equal to 1. And therefore, P is equal to A squared plus B squared. Well, P is equivalent to 1. Since P equals A squared plus B squared, and I'm going to say since this is A squared plus B squared. So 1 well, it's not literally A squared plus B squared, but so we showed that this was A squared plus B squared mod 4, so yeah, everything checks out. I wonder if there's another way to do this part, where you don't have to actually like descend into division and all that. But yeah. Okay. Okay, 7. Let's see how we're doing. Oh, hour 40. Yeah, we're doing very well for only an hour. Okay, prove for all a and n, then a to the n is 1 mod a minus 1. So let's say, suppose a is in the integers and n is in the natural numbers. We will show that a to the n is equivalent to a minus 1, 1. By the definition of equivalence, this is, it suffices to, not equivalence, congruence. It suffices to show that a minus 1 divides a to the n minus 1. Oh yeah, there are a couple ways we can prove this. One is where this is going. And we'll do 2 of these. So, recall that a to the n minus 1 is a minus 1 times a to the n minus, so n, all right, n is not necessarily positive. Might be 0. So this formula does not work for n is 0, and we need to check that separately. Unless there's some silly thing that I'm not thinking of. And there's another thing that we, well, can we do that? Well, one of the ways, like what we're really going to be using is that whenever you have a polynomial that has a root, then it's divisible by that root, or then by x minus that root, or in this case a. And so if we plug in 1 for a, it's definitely 0, right? So a minus 1 is a divisor. This is like something you might have seen in calculus and maybe even algebra. Well, let's just do cases. So case 1 is n is 0. Case 2 is n is greater than 0. Well then a to the n minus 1 is a minus 1, and a minus 1 divides a minus 1 by reflexivity. N greater than 0. Then we can use this formula. This is probably also where I'm going to realize I did not need to do cases. Well, first of all, we had that. It's not reflexivity. Oh no, there's an error. Oh, where'd the end of the description go? Right, so it turns out this formula actually is just fine, because when n is 0, well, when n is say 2, then we get okay, let's see. If n is 1, then we get a minus 1 times 1, because yeah, okay. I need to write a sigma to give you the right interpretation. But so yeah, it's this. That a to the n minus 1 is a minus 1 times the sum of I equals 0 through n minus 1. Also, I don't like writing it like that. I like writing inequality notation. So, which is still valid when n equals 0. Okay. So, what's the point? Well, hence, by the definition of divisibility, we've shown what we wanted to show. A lot to say about nothing. Let's add a we have. I want to push this to the next line, so I just added some words. Okay, proof 2. The way this is notice that A is congruent to 1, since by reflexivity we have that. So what? Hence, a to the n is equivalent to 1 to the n, which is equal to 1, which is what we wanted to show. So let's copy the first line to make it a fully specified proof. And then that's that. That's the first proof I actually wanted to write, but I went through this first one because, well, it's a good one too. Okay, we're in the home stretch. Or maybe it's the second to last lap. Find the least positive k such that 3 to the k is 10. Now that we know about Fermat's little theorem, I guess we know this has something to do with that. We know from that that we know nothing, actually, because 10 is not prime. Let's make a table of 3 to the k after dividing by 10. Let's see. I wonder why I did left or right. I got left and right backwards back there. Oops. So the first will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We do not need to go that far. Let's go this far. So k, 1, because we're only considering positive k. So that's k, and then we got 3 to the k mod 10. Well, first, oops, I forgot a new line there. wonder if this is clear if I put an H line, horizontal line between them. Yes, yeah, why not? Okay. First number, 3. Then to get each one, we can, wait. Five's a handful, right? So each successive number here is going to be from multiplying by 3. So 3 times 3 is 9. And then I'll use my tricks. 9 is minus 1 times 3 is minus 3, which is 7. 7, well, that's minus 3. Times 3 is minus 9, which is 1. And then if we multiply that, so by merely looking at the table, we see that k equals 4 is the least with this property. There's no reason to say positive natural number, just positive integer. And also, by the way, merely, it's just an old-fashioned word for purely, I believe, which is why I used it. Not because it's old-fashioned, but because, I mean, just by looking at the table. So using this k, let's prove this. That we have this exponentiation reduction law, just like in lecture, but for 10. And what's important here is just that 3 is co-prime to 10, and that's why it does get back to 1. Solution. Proof. Okay, suppose m is in the naturals. There are a couple ways we can do this. One, we can do induction on m, but then you have to deal with this case of whether or not m is like 3 mod 4. It's not so bad, but I don't want to do that. You know, it's already an hour 52 in. Suppose m is in the naturals. We will show that 3 to the copy paste is true. We have that 3 to the m is equivalent mod 10. Well, it's actually just equal mod 10 to 3 to the power of m. What do I want to say? It's just the division theorem. So let's let q equal the division, so it doesn't have to be up in the exponent. Okay, so that's how I'll phrase that. So letting that, we have that, I want to divide by k. And we're using our particular case, so let's write 4. So we've got 4q plus m mod 4. And there is an error. L4. Great. So this equals 3 to the 4 to the q times 3 to the m remainder 4, using just some exponentiation laws. And then let's create a tab stop right here. Let's see what this is congruent to, because we showed that 3 to the 4 was 1. So we can replace that. And this is not an equals, but equivalent, yeah, congruence mod 10. And that is 3 to the power of n remainder 4. Yeah, so that's that. So we've got these equalities running through this congruence mod 10, so therefore we have shown what we wanted to show. Okay, next part. Let us calculate 3 to the 2022. So the idea is that, okay, so this number being divisible by 10 is equal. We'll say this later, but it's equivalent to being at 0 mod 10. So we'll just, create the fact and then interpret the fact. Never let your audience know what's coming next. Not really good advice, but it's a short proof. So I just am for some reason not wanting to divide this by 4. I can do that. So that divided by 4 is 5. Go 5. I think that's right. So 505 times 4 is 2020 plus 2. Okay. So then by this rule, oh wait, this was just equality. I guess first I'll just say, since we have this, then 2022 remainder 4 is 2. So then we have that. That this is 2022 remainder 4 plus 1, which is 3 to the 2 plus 1, which is 9 plus 1 is 10, which is 0. So a number being divisible by 10 is equivalently that it is 0 modulo 10. So by the above, we have that 3 to the 2022 plus 1 is divisible by 10. That sure beats multiplying out 3 to the 2022. Though, really, well, yeah, we're just noticing the pattern that it loops after 4. So we're using the remainders to cut that loop short. Or just jump to the end and see what happens after we do all of our 505 full loops. Okay, we're finally in the home stretch. So there's this hint. You can read it if you want. So for this, prove for all m and n with n greater than or equal to 1, the product of 1 minus m and this other thing is congruent to 1 modulo m to the n. Because, so the Taylor series expansion of 1 minus m to the minus 1, it's the infinite sum version of this polynomial. And so sort of the point is that when we're doing things modulo m to the n, then this series gets truncated, because from that point onward all the terms are 0. So we can take that infinite sum and just compute it now, because it's finite, and then because it's supposed to be the inverse, it's the inverse. So that's sort of like the intuition. But, you know, we don't really need to worry about that. Also, I guess technically we should be doing like induction or something here, but okay. So suppose m and n are the natural numbers with n is greater than or equal to 1, then so we have that. I'm going to write this in sigma notation. So 0 is less than or equal to I is less than or equal to n minus 1 of n to the I is equal to, let's distribute, yeah, like there are different ways you can do this manipulation. I'm just doing one way. So I brought the m in. Then, let's do an intertext. I think that's what it is, to put some text between multiple equations. So what we're trying to do is, let's see, does this render? Yeah, that's an intertext. I want to get these exponents comparable. So letting I plus 1 equals j for the second sum. Get j up there. Now we have to transform this inequality appropriately. So let's see. We solve for I, and that's j minus 1. And then we can add 1 to everything to get that. Let's just show most steps. So we can take 1 plus, pop it off the front, and then pop 1 off the back. And that's 1 minus m to the n. Long story short. Okay, so hence, since m to the n is congruent to 0 modulo m to the n, then this product is congruent to 1 modulo m to the n. Right? Well, that's how I like to manipulate it. Sigma's a little ugly, but when you get used to it, it gets the job done. And also, like, what this is all hiding is that if you take this thing, I'm just going to do it again. Because I have this other picture in mind. But it just, you have to be careful because it's ... notation. You just never, yeah, you have to make sure that you get the pattern all right. Which is what sigma is all about. So we have that, minus m that, and then we bring the m in. See, this is where we need to know what the rule is, which is what sigma is all about. And then we have to somehow do this shuffle where really we should, yeah, this should all be with induction to do it properly. Let's see, this is a good induction proof. Because the induction hypothesis would be if that they're congruent to 1 modulo m to the n, then it's congruent with the next term added to 1 modulo m to the n plus 1. And so I guess we can try it. I'll just write this. Well, that's the idea. Except, of course, it's too wide. There's usually not that good of a solution, or I don't know how I want to. I usually have to resolve how I do this. Well, I definitely want the ampersands. So maybe it's not quite so clear, but so being a bit hand wavy with the ellipses. Okay, so let's see, what would the induction proof be? So we would want to show that the next sum is 1 mod m to the n plus 1. But we only know what it is, m to the n. So if we reduce our equation, mod n m to the n, then that would kill the last term. Well, you can figure it out. Let's get done. So, prove. Suppose m and n are natural numbers with n greater than or equal to 1. We will show the conclusion. Okay, so there are two things we can do here. We can do, let's do my intended solution. Because it's kind of a nice little observation. So this is equivalent to m to the n. Oh, right. I'm forgetting. So, okay, so the idea was that if you got a system, or I mean like just a equation, like ax plus, by equals 1, I guess, then okay, I think this was the idea. This is proof 1. So m to the nx plus that y equals 1 having a solution. I guess that's just Bayes' identity. So what? Well, we saw in A that, okay, this is equivalent to this having a solution as a congruence. So we saw in A that y equals 1 minus m is a solution to this. So so there's that. So taking the GCD, turning it into some other problem, and then recognizing it. Let's do another proof, one that you might have come up with. Is this one's kind of a, it's sort of indirect. So we have that this is equal to we can take this and add or subtract a linear combination from another part. Oh wow, that is wide. So letting, let's just say k equal this, we have that is k. Is this what I want to do? Because, okay, what's the idea? So this times 1 minus m is 1 mod that. So I'm not sure why I would add this to that side. So thinking, how is any other proof really going to be fundamentally different from the first one? Well, there's some other thing that might work. So we got that, like before. Instead we add into the n to it. Oh, I guess the other thing is no, I'm not sure. Okay, so we got the product of that and that is 1 plus some multiple of m to the n. Well, let's see. So letting this, we have that there, we have by A that 1 minus m k is equal to 1 plus h m to the n for some h in z. So going back to the first idea, this GCD. I guess I was thinking maybe none of this makes any sense. But I was thinking, okay, so if we could then substitute that in and get h plus 1 times m to the n plus 1 and then k over here. Oh well. Well, that was fun. Watching, I guess, just me kind of mutter to myself for the past few minutes. But this was like the main idea I had. I thought there was another way to do it, but you know, this is midnight math. Okay, like, you know, the right way to do math is not just sitting down and just powering through, not taking any breaks, and also like talking to yourself the whole time. You know, it's good to take breaks. It's good to think about what you're doing, come up with new ideas. I guess the best I can say about this is, well, I thought about it last week when I wrote the homework. Well, let's look at everything, make sure nothing's missing. So, just skimming through. Well, thanks for joining me for Midnight Math, and hope you enjoyed seeing some of these solutions, and good night.